Hello, I'm Reem and I'll present our paper, Doppler volume rendering. First of all, I think we're all more familiar with Doppler effect when it applies to sound waves. For example, when you are standing in the road and a car is approaching you, you can hear its pitch going like mm. That's Doppler effect. Doppler effect can also be applied to light waves. However, instead of being perceived as a change in the pitch, it's perceived as a change in the color. For example, when the object is moved in a certain direction, the waves in that direction are compressed, causing a blue shift in the spectrum. Similarly, the waves here are stretched, causing a red shift in the spectrum. Although they're called red and blue shift, the object doesn't really become more blue or more red to our naked eye. It just means that the spectrum is moving to the left or to the right. That's because Doppler effect actually depends on the speed of the object that's moving. This is why Doppler effect shines when dealing with data of extreme physical magnitudes, such as dealing with stars and galaxies that move at hundreds of kilometers per second. It also has many applications in astrophysics, such as figuring out the speed of the star based on how its spectrum was shifted. Also, astrophysicists do 3D simulations like the evolution of galaxies or the merging of black holes, and they need to physically visualize those with Doppler effect taken into account. And so, our goal is to, in real time, apply Doppler effect to volumetric data of galaxies. The main contributions of this paper are: first, to the best of our knowledge, we are the first accurate Doppler effect computation in interactive volume rendering. Secondly, we adapted the spectral volume rendering using two different emission models, the thermal radiation and the line emission. Thirdly, we proposed a novel, dynamic, piecewise linear representation of the spectra that overcomes some of the drawbacks of the traditional point samples representation. Lastly, we implemented our proposed technique in the GPU. Our system, in a nutshell, aims to visualize Doppler effect applied to volumetric galaxy data in real time. To do this, a volumetric galaxy dataset is taken as an input, which contains the star densities and the information necessary to get the spectrum. In addition, a velocity field is essential for Doppler computation. Then, we are going to take this data and visualize it using spectral volume rendering, while applying Doppler shift to the spectrum using the given velocity field. Most importantly, the spectra in volume rendering is represented using our proposed piecewise linear spectrum representation. In terms of spectral volume rendering, it's an extension of the traditional volume rendering. However, instead of accumulating RGBA values, we work with the spectrum directly throughout the rendering process. Every volume element can emit and absorb light at any frequency of the spectrum. And then once we exit the volume, we convert the spectrum into its corresponding RGB color. Spectral volume rendering aims to address the shortcoming of the RGB color model, and it has many advantages for our purposes, such as it offers more realistic optical effects. In addition, it's physically correct representation of the light flux. Also, transparency now depends on the wavelength instead of depending on the alpha channel. Finally, it can deal with electromagnetic emission outside of the visible range, like the infrared or the ultraviolet. Regarding the spectra and astrophysical data, light radiance comes from the matter, both as thermal radiation or as photon generation. Thermal sources are modeled using an idealized blackbody. In physics, an idealized blackbody is a source that emits radiation based on its temperature, and it doesn't absorb anything. To compute the spectrum of a black body, Planck's law is used, and as you can see, it only needs the temperature to compute the whole visible spectrum, for example. That's why a temperature scalar field is important in the data. The figure here shows the spectrum of different temperatures. As you can see, its peak is moving to the left as the temperature increases. That's why the color goes from red to blue as the temperature increases. Our sun, for example, can be modeled as a black body with temperature around 5,500 Kelvin. The other model is photon generation by free charged particle acceleration. Different materials absorb and emit lights differently due to the chemical nature of their components. In this case, the spectrum is given as emission and absorption line. For example, this is the hydrogen emission line, while this is the carbon emission lines. Although those emission lines look like delta peak like, they never occur like this in nature due to the different broadening effect like the thermal broadening or the pressure broadening. Now we have our volumetric dataset with the velocity field. We also got the temperature to compute the thermal radiation, and we got the lines for photon generation. And then we are going to take this as an input for spectral volume renderer, and then apply Doppler effect to the spectrum to get our final result. Now it's time to talk about how to represent the spectra and how to actually do Doppler spectral volume rendering. A simple approach is to apply Doppler effect to spectral volume rendering would be to use the traditional point-sampled spectral model. In this model, we divide the spectrum into N bands. For example, this emission line spectrum will be mapped into this band spectrum. Then, at every step along the ray, we sample the density and velocity, and then we apply Doppler effect to get the shifted spectrum. For example, you can see here that the spectrum was redshifted and the intensities were scaled accordingly. We are going to get a spectrum like this at every step along the ray. And to accumulate them, we just add them on top of one another, because the spectrum are additive. And then once we exit the spectrum, we just convert them into an RGB color. However, this model has many limitations. First, it could over or underestimate the Doppler effect. If the Doppler effect fell into the same bin, it will be underestimated. And if it was shifted only slightly but fell into the next bin, it will be overestimated. Secondly, we can get a loss of energy conservation. For example, two lines could fall into the same bin despite being quite far away, resulting into an unwanted peak. Similarly, we could get an unwanted absorption line. In addition, if the lines fill out of the bin range, then we lose information. Lastly, the spectrum depends on the number of bins. For instance, those lambdas here are merged into one bin when dealing with 40 bins instead of 400 bins to represent the spectrum. And so we propose our piecewise linear spectrum model. We model the spectrum as non-overlapping line pieces. And then at every step along the ray, we sample the velocities and densities twice, and then apply Doppler effect twice, giving us a linear piece that look like a trapezoid in the spectrum. And we're going to get a spectrum like this at every step along the ray. However, accumulating them now is not as easy as adding them up anymore. We need to think of how to accumulate them. That's why accumulation is the most expensive part of this algorithm. Given two pieces, for example, there are around 11 cases of how they should be added together. In short, the piece will be broken down at every overlapping point, and the overlapping point will have their slope and intercept adding on top of one another. And this process will continue until no overlapping pieces are left. And as you can see, this is a very recursive process. That's why it's the most expensive part of our algorithm. Then, once we get the final spectrum, we should convert it into an RGB value. However, we can't do this directly, so we convert it into an XYZ value, and then we can convert XYZ to RGB trivially by linear transformation. To do the spectrum to XYZ conversion, we model the CIE functions, sensitivity functions, into our piecewise linear model as well. Then, their integration will simply be multiplying two linear pieces, giving us an easy-to-implement equation. Finally, for our results. In terms of implementation details, all of our tests were done using a PC with Intel processor and 128 gigabytes of main memory. We ran this on Ubuntu 20 OS. The graphic card was NVIDIA Titan RTX with 24 gigabytes of memory, and our code was written in C++ using CUDA 10.1 and OpenGL 4.6. For our implementation, we used the Sormani dataset, which simulates the asymmetries in the innermost region of the Milky Way. We resampled it into a uniform grid of size 128. The dataset comes with black body density and different material densities like hydrogen density, carbon density, and in addition to the velocity field. Here's a visualization of how the dataset looks like. For example, we got the black body density, the black body temperature, the different material densities and their emission and absorption lines, in addition to the velocity field. Now for our results. First, we show how our model look in black body emission without Doppler effect. When we select a point, we can look at how its spectrum looks like. For example, this is the spectrum of the selected point, and you can see that its peak is around the green region. It doesn't mean that it will look green to us, it's just its peak is in the green part. And then, when we apply Doppler effect, we can notice how the peak is shifted in which direction. For example, the peak here was shifted to the blue direction, denoting that this part is getting closer to the observer. So this part here is getting closer to the observer, and the other part is getting further away from them. And if we choose a point that's getting further from the observer, we can see that its peak is around the red, the green, yellow region with Doppler effect. And without Doppler effect, its peak is now on the blue side. So that means that this point was redshifted, so getting further from the observer. In addition, we can look at the line emission result. And then when we select a point, we can look at its spectrum. This is the result of the hydrogen emission and absorption. When applying Doppler effect, we can see how the spectrum was redshifted. In addition, we got broadening effect that we want. If we select another point, for example, this point here that was redshifted, we can look at how its spectrum looks like. And we can also see how the spectrum was accumulated along the ray. If we chose a point that was blue shifted, we can also look at its spectrum and at how its spectrum was accumulated along the ray. We can also apply black body emission and line emission on top of one another and look at how the spectrum looks like with and without Doppler effect. If we selected a point, we can see how its spectrum looks like. Now, to compare our solution to the point sampled one, we notice that the point sample spectrum has higher energy compared to our solution due to the loss of energy conservation discussed earlier. This is also reflected in the resulting image. In comparison, our model is more accurate, and also you can see the trapezoidal shapes in some of the peaks. To test this more accurate claim, we render our solution and compare the image difference to the solution given by the point sampled solution with 40 bins, 400 bins, and 4,000 bins. And we notice that our solution is the binning solution gets closer to our solution as the binning size increases. Lastly, to optimize our method, we proposed a merging mechanism. When two neighboring lines have close slopes and intercept, they are merged into a piece. This improves the performance and reduces the space needed to store the spectrum at the cost of the accuracy. For instance, by increasing the tolerance, we noticed that the number of pieces went from more than 1,000 to 100 pieces only, and the time was also improved by a lot. However, the accuracy was heavily affected. This is useful when there are so many emission lines that will never be able to render in the GPU unless we decrease their numbers. In terms of the performance, we record the time it takes to render a frame. In this figure here, for example, you can see the spectra of the selected point with and without Doppler effect. For the blackbody model, the rendering time was optimal and with and without Doppler effect. For the line emission model, however, the time it takes to render the image depends on the number of emission lines. Since the accumulation is recursive, rendering the hydrogen only, which has the fewest number of emission lines, takes 1 second with Doppler effect. However, when we try to render more materials with more emission lines, this affects the performance heavily, but the renderer is still able to render the results. But when the density is too great and the number of emission lines is just so huge, the renderer isn't able to render the results anymore unless we increase the tolerance in the merging optimizer. In conclusion, we modeled Doppler effect in spectral volume rendering using piecewise linear function in real time. Our representation is more accurate and efficient than the point samples representation. However, it needs further optimization to scale. This can be accomplished, however, using large-scale data techniques available in the literature. Thank you for your attention.